they're going about 8,000 miles an hour. It depends on the system, and it depends how precise you want to be. But for our purposes today, they're going 8,000 miles an hour. So we don't want to describe that as an XYZ. We instead provide that as a Keplerian orbit descriptor that describes the path, and then we look for points along that path as we're doing the calculations. We actually have to do a little bit of relativity in here. So for those of you that thought you were doing measurements on a crash scene, you actually do need to worry about relativity as well. Unfortunately, you don't, because somebody has worried about that in the receivers, and we have to make corrections for the speed of the satellites, and we have to make corrections for the gravitational potential of the satellite height as well. The signals are extremely weak, so the transmit level from a satellite depends on how much power you can have in the satellite, which you can only garner from solar energy. So the satellite looks as though it has wings, which it looks as though it's flying with enormous great wings, but those are solar panels. Their sole purpose is to capture the sun's energy. And that energy is the only thing that the satellite can use to make its transmissions. So the transmissions from GPS satellites are around 50 watts. So these beasties have a radio signal, which is effectively the brightness of a not very bright electric light, and they are 20,000 kilometers away. So as you will imagine, the signal is not very strong when it gets to us, and it's only through the magic of spread spectrum signal processing that we can recover that, because it sits below the radio noise floor and has to be extracted. As well as that complexity, the user will be moving. The signal transmission environment includes disturbances, and it delays the signal so that the signal doesn't universally travel at the speed of light. There are objects which can obstruct the satellite signals and attenuate them. There are objects that can reflect the signal so that the path that we've measured is not quite correct because it's bounced off a building. There is also radio noise, and there is potentially interference in to that radio signal. And all of that environment is also changing. On top of that, the users don't want the XYZ that we just calculated. They never want that. Latitude, longitude, and height is often wanted, or a conversion to the Ordnance Survey grids. But all of that can be done, and it works. So all of that is solved. In summary, the satellites are carrying precisely synchronized atomic space clocks, which have been corrected for relativity. And we accurately know where the satellites are. A receiver takes measurements from multiple satellites and correlates those signals to measure the pseudo ranges. The pseudo range is the name that we ascribe to a range plus the clock offset. And we then solve that for the four unknowns of three-dimensional position and time. And we can also get velocity out of that by measuring the signal Doppler. I have a brief look, and I'm just going to pause for a second, because that is most of the signal, most of the system complexity that we're going to discuss today. So I'm just going to pause for an instant to let people get their brains straight again after probably looking at a domain that many of you won't be all that used to. Okay, that's enough of a pause. In terms of the architecture, this is obviously what folks are more familiar with. There are satellites transmitting a radio signal to users, and those users may be in cars, with handheld devices, on ships, etc. But there is also quite a bit more of a system. There are sensor stations. They have different names for different systems, but in Galileo terms, as I mentioned, I was involved in the development of Galileo. They're called sensor stations, and a sensor station is doing a very similar job to a receiver, but it's then dealt with in reverse. So there are about between 30 and 40 of these placed at precisely known locations around the globe. They take a measurement from the satellite, but their location is already known. So what we then do is take measurements from several precisely known user locations, and we do a reverse GPS to work out where the satellite was at its time of transmission. That's relayed to a control station where the information from about 30 satellites, so Galileo has just under 30 satellites. The design intention is that it will have 30 in due course. 30 to 40 ground stations taking measurements on all visible satellites, which may be 8 or 10 visible satellites. So an awful lot of measurements are mashed together and sent to the control station, where that is put into the reverse nav equations. They're called orbit determination and time synchronization equations, where we work out the satellite motion. And we then relay that on a satellite link up to the satellites to tell the satellites precisely what their clocks are doing and their precise orbits. And that information is included in the message transmitted continually by the satellites. So the whole system is monitoring itself and continually correcting. There are now quite a selection of GNSSs, and all of them are free to use a civilian service of. There are, for most of these systems, there are military grade services, which you have to be a friend of that military in order to use. So we won't bother with it in this forum. We're only interested in the civil version. They're global. They provide coverage over the whole Earth, pole to pole, all around the equator, north, south, east, west, everywhere. And continuously, 24/7, non-stop, continuous transmissions. The receivers are extremely low cost. Not many years, well, okay, so I've been working 35 years. It probably is 10 years ago that the folks that made phones were reliable. The big daddy of these systems is the American GPS, arguably the best of these systems, certainly the first of them, and the one that all others have to measure themselves against. It's been operational since 1995, and I should qualify what we mean by operational. So what that means is that the US government has monitored the GPS transmissions, has checked with the guys that provide excuse me, the guys that provide the service, that everything is set up and stable and etc. And once they are convinced that their specifications are being met and are going to continue to be met, they declare that the system is operational. So GPS has actually been operational for quite a lot longer than that, but in terms of a formal declaration, 1995. So we have a long heritage with that now. Since then, there have been many more satellite launches, upgrades to the ground segment, and so on. So it is continually upgrading and modernizing and continues to be reliable. There is a broadly equivalent Russian system called GLONASS. There was a little bit of a race in the 90s to see who could get their system operational first. Russia was a year or so behind in terms of the completion of the system and it becoming fully operational. A few years after that, there were various difficulties in Russia, and Russia had to look again at its finances and decide where it wanted to spend its money, and the system almost failed. The number of visible satellites, the number of satellites in the whole constellation dropped from 24, 25 to 7 for the whole globe, which is not enough to navigate with. Now, since then, they've reallocated funding to it. The program is up and running, and GLONASS is now a fully working system as well. The Chinese have a system, a much newer system called Beidou. They have essentially looked at what these other superpowers are providing, and they thought, well, we should have one as well for the reasons that, you know, that these are the civilian reasons, the ones I've highlighted here, you know, extreme accuracy for a very low cost piece of equipment. There are military reasons as well why somebody may want a GNSS. So the Chinese system, Beidou, has been brought into existence and has been fully operational now for more than a year. It is the same as the others in terms of satellites transmitting a radio signal and uses the same sort of orbits. MEO orbit, medium Earth orbit, is about 20,000 kilometers, and that's the main one that the Chinese use as well. But they also use a much larger geostationary orbit. Geostationary is a particular altitude at which the rotation rate matches the Earth's rotation rate, so the satellite appears to be stationary when viewed from the ground. So the thing that the Chinese have done is to put some additional satellites in a geostationary orbit over China, thereby enhancing the coverage over China. And Europe has its own system as well. This system highlights the difference between full operations and operational. So the system has been operating and transmitting usable signals since 2016. So there's been a useful constellation which can work on its own and be useful for navigation. But even more interestingly, it can be used with GPS and other systems. So that has been the case now for 6 years, but it will only be later this year that the system finally is declared fully operational in sort of the political terms of the constellation. The other arguably interesting point is that this is the only non-military system, and that used to be a very interesting selling point, if you like, for the Galileo system, except that obviously as a user you can use something from all of these other systems as well. I have also spent part of my career working in the defense industry, and I can assure you that as defense industry, we are also looking at the use of Galileo, and it is extremely likely to be used militarily, even if the system itself is not strictly a military system. Now, when you put them all together, you get this very dense mesh of satellites. So each of these systems will have between 24 and 30 orbiting satellites, all orbiting in very similar orbits, except for the geostationaries from the very few, I believe there were, I'm not sure if there were 2 or 3 in the Beidou constellation that are geostationary. Now, the reason for mentioning this is that there is equipment, including mobile phones, easily available to us, which uses all of these potential measurements. Now, in terms of how they move. This is you'll see the compass points on here. And this, if you think of this as a dome over a user, where the center is directly overhead, and then we have down to the horizon. You can see satellite G06, for example, GPS number 6, as they've called it here, is at a very high elevation, about 80 degrees in the east, and it has come from the south. So it has been rising and moving from the south. So at a particular location, that is the motion. This other satellite 19 is now in the north and moving towards the east, but is descending. So that is a snapshot which I haven't got the numbers in front of me. I believe that is an hour of satellite motion there. So everything is in motion, and the green bits that you see on this slide are just the GPS. So you can imagine with all of the other satellites, there's a very dense signal environment. Now, in terms of use, there are very many markets, sectors, however you want to describe them. Probably the most interesting for us is this left-hand one: road transport, intelligent transportation systems, insurance. We very often delve into this zone of location-based services and wearable technology. So things like sports equipment, so classically your Garmin cyclists unit would be in this sector, and mobile phones would also sit in that sector. I really don't know how much really the traffic accident investigators get involved in shipping or air crashes, but they use the same. I mean, they crash, and they use the same equipment for navigating. They use the same background system, specialized receivers, of course, but they work on the same principles, and the performance ends up being very similar. So they're used in different ways, and because of the additional necessity because they're carrying such big cargoes or such big numbers of passengers, there's a whole load of extra safety and security concerns. In terms of navigation, they're using very similar technology, and the background systems are identical. And of course, there is, as we all know, there are now drones, be they flying drones, be they Mr. Tesla's cars racing up our motorways, be they farm machinery that is plowing very straight lines with no farmer in sight. All of that is using GNSS to do its job. I've looked at 3 different systems different devices to delve into what I believe is probably of most interest to this community: car telematics, sports trackers, for example, a cyclist, and a mobile phone, which everybody has a mobile phone. If there's anybody today that doesn't have a mobile phone, please identify yourself, and I'm sure everybody else will be surprised. And all mobile phones have GNSS chips in them, and the US military aren't spying on you, but Apple and Google certainly are. Now, in terms of what there is in car telematics, so I'll go through those one at a time. In terms of what there is in car telematics, there is a device which very likely will be combined with accelerometers. And the accelerometers, as it says on the tin, they measure the acceleration. So they're particularly interesting at a crash scene. measuring precise decelerations in that environment. I'm not going to delve in this talk into what the accelerometers do. I'm sticking with the GNSS, which is not useful for that ultra-fast deceleration, but will describe what the vehicle was doing running up to the collision. Was it traveling within the speed limit? Where was it on the road? And so on. In car telematics, there are very often additional sensors. There are ignition sensors, there's gear detectors, there's door sensors, there's things monitoring the tire pressure, all of which gets fed into the car's internal bus system, the CAN bus telematics control unit. From the telematics control unit typically over a mobile phone network, to what I'm referring to as a telematics data company. Might be a car company, might be a telematics data company, might be an insurance organization. But they have a big store of data, and they will do additional processing on what they receive from their huge fleets of vehicles. The main types of these, there are manufacturer fits and there are aftermarket, typically for insurance purposes. The manufacturer ones are generally put in when the car is built, and they might not be optimally placed for GNSS signal reception. Now, the GNSS, as I described, is a satellite system, so the signals are coming in from above and indeed from all elevations. You can optimally place an antenna to receive those signals. Not everybody does. Sometimes the life is made incredibly difficult for the GNSS in terms of that. The data sets of these manufacturer fit devices are incredibly complex because they have tire pressure, gear that the thing is running in, the revs per minute, and a huge amount of data is in there, which gives us the challenge of trying to find the bit we might interested in if what we're interested in is position, speed with timestamps. Aftermarket units are very commonly fitted by for insurance companies. The start of these, they would get garages to fit the unit. They would get somebody that actually knew what they were doing to fit the unit either under the bonnet or somewhere else in the car. For cost reduction reasons, they are increasingly moving towards a self-fit unit for the customer, either to plug into an OBD port of the vehicle or even into the cigarette lighter. So that is now sitting inside the passenger compartment of the vehicle. And maybe in terms of the OBD port, that is very commonly close to or part of the central steering column. So there may well be quite a bit of electronics and metal in the immediate vicinity of that unit and stopping it getting direct signals. So this affects the accuracy that we may get from these because of their suboptimal placing. And the data, as I said, the data sets are very rich, and finding the wood amongst the trees can be a challenge. Can be achieved, but we get huge data sets. The worst data set that I have seen was sent to me through DHL by an insurance company, and they sent it to me through DHL because it was contained in 3 large boxes, and it was paper printouts of hundreds of pages of thousands of elements of telematics data, and they sent this to me at the essentially the pre-instruction stage in a crash investigation to say, can you, Dr. Dixon, can you please tell us what was happening? Usually not quite as bad as that. Right, then the next sensor, sports monitor. These are by runners, by cyclists, potentially by other sports as well, and may be interesting to us if such folks get involved in accidents. The sports tracker unit, there's a front display shown there, saying display screen, which is mounted on the cycle, generally on the handlebars, generally mounted in a position so that the cyclist can see it, because it probably is also providing some route guidance for the cyclist. Just a name job as a car sat nav. And that location of it means that it also is very nicely placed for the reception of satellite signals. So we actually find these units are often very accurate at describing the location and time of the user, and consequently the velocity of the user. There are often additional sensors as well, things like a cadence sensor telling us about the pedal motion, or the wheel motion. A heart rate monitor is very often used as well, so we end up with a much lesser set than we do in car telematics, but a little bit more than we would get just from GNSS data. The hardware that is produced here, its central purpose is navigation and tracking. As a consequence, and for those of us involved in this, it is generally done very well. The antenna, the receiver, and so on are generally of very good quality, which is great for the sportsman. But in the event that that needs to be used evidentially, it usually is of very high quality as well. There's a little bit of additional data in terms of this, not just the positioning data. Generally, it's stored on the device. It may also be relayed to either the manufacturer, so someone like Garmin, a whole stack of this data. It may be relayed to a sports company, Strava, for example. May be relayed to Apple, Google, whoever is the phone company. And as I said, the equipment is usually first class, and the little bits that we need to be wary of is that they do some data compression. So if the cycle is going in a straight line at a constant speed, they calculate its location, perhaps every second, along that straight line at constant speed. And then they say, it's going at constant speed in a straight line. We don't need the in-between points, and they take them away from the stored data. So we now can only assume that that was done. We haven't specifically got all of the points. So some data elements get removed. Sometimes there's also resolution compression, which results in an accuracy degradation, and sometimes numbers get rounded or truncated. We can cope with that, but we need to know, were they rounded, were they truncated, and where were they rounded or truncated, in order to understand what is the resultant accuracy. For those of you that have forgotten what a smartphone looks like, that's what a smartphone looks like. And on the inside, it looks a little bit like that. That's a particular manufacturer of smartphone whose logo I've disguised cunningly here so that a lot of the phone is taken up with the display electronics. A lot of it is taken up with the battery, which has to deal with all of the very many things that modern smartphones deal with, and part of it is dealt then with the electronics, the main electronics of processing for calls, for communications, for data access, and one chip, typically only one chip, that will deal with all location parts. So GNSS will be one of the technologies contributing to the phone's ability to position itself. It will also use Wi-Fi technology, cell tower positioning. It will have accelerometers in it. It may use beacons. They're relatively widespread in the US and relatively rare, or extremely rare rather, in the United Kingdom and other places. I appreciate we have an international audience here, so I don't know how widespread things like iBeacons are in other states, but I know they are very rare in the UK. But those again can be used by phones for positioning. Now, in terms of the hardware, unfortunately, as a long-term, unfortunately, navigation is very often unimportant to the device manufacturer. It's an afterthought. They have to include GNSS because their rivals include GNSS, and their customers will say, "Well, I'm not buying the latest iPhone because it doesn't have GNSS. I can't position as I used to." But it's not one of their prime things. It doesn't compare with internet access, 3G, 4G, 5G, phone quality of the camera. So the implementations are of variable quality. The antenna and the receiver are ridiculously cheap. I mentioned sub-dollar, and that is certainly not increasing these days, even though capabilities are increasing. Now, that's not the same as poor quality, but it can mean that there are quality compromises. And one of the things that we certainly see in phone design is where shall the GNSS and be in relation to other antennas that are used for communications, including communications transmission. Obviously, a phone is no use unless it not only receives but transmits. So the weak GNSS signal, the light bulb from 20,000 kilometers is coming in. The phone is not only receiving a 5G, 4G radio signal, Wi-Fi, etc. It's not only receiving that 2 miles away, but it is transmitting from a centimeter away. So one of the difficulties that we repeatedly see with these devices is that they self-interfere. The transmitted signal can cause a problem with the reception of the GNSS, and it's something that the phone manufacturers don't yet seem to have learned, and seems to be a crisis, not with every new design of phone, but very often with the design of new phones. Our chip, as I mentioned, includes a whole array of different positioning capabilities. Regrettably, it doesn't always identify what is the source. Sometimes I'm not going to name names here, iPhone, but certain manufacturers tell you if they produce a position, they will tell you that it's a GPS position, when it's a GPS position, and when it's not a GPS position. Not helpful. And then there's the users. The users of a mobile phone do ridiculous things. They put the phone in their pocket. They put their phone upside down, even though the GNSS antenna is at the top. They put the phone in their handbag, in the glove box in the car, falls into the footwell in the car. So all of this is a nuisance. Very often there's still a recoverable position, but it may be of degraded quality. In terms of the data, it's nearly always stored in the cloud. So by the phone company, by the phone manufacturer. It is a very rich data set that includes all of the other things that a phone can do, as well as the PNT data, the navigation data. And so you have to extract the PNT from that. Privacy is sometimes an issue with this, making data extraction very difficult in some cases. And sometimes there is no cooperation at all from the provider, even for the provision of such data for the forces of law, when confronted with court orders to solve major crimes, and even in the event of the death of the phone's user, privacy is sometimes used to stop access to the data, which is shocking, but is a fact. At its best, this data is as good as the sports monitor, with a load of extra data telling you, what else the phone operator was up to. The phone user. In terms of the data, what does it look like? What does it mean? Can you rely on it? Best, worst, and some tricks and traps. So the best that you get is a breadcrumb trail, 1 per second. So on the right-hand side, there is a map, and overlaid on the map are a whole series of little dots of the motion, in this case, of a cyclist. And cyclists traveled from the north to the south, down across this park, and then along the main road, past the football stadium. There is an incredible density of information. Now, if we needed to look at an accident that had happened, now in this case, an accident had happened, which how come I have the data, but not this part. So I've picked a non-controversial part of the data. But you can imagine if there had been a collision as the cyclist traveled across the park, we have an incredibly rich data set from which to extract exactly what was the location. The data in this case is so accurate that we can tell which side of the path they were traveling and get some very precise information on the speed as well. That may be augmented by accelerometer data, particularly in the case of things like telematics, and in particular in the case of telematics in the event of a collision. Records less than 1 per second may also contain all of this, incredibly rich data. It really gives us a deep insight. This is the kind of thing that it looks like, or when you turn it into a table, this is what it looks like. So the first 2 elements are usually referred to as the timestamp, the date and the time. Those are nearly always, and we hope that they are always, derived from the GNSS. So the GNSS, as part of its position calculations, calculates very precise time, and therefore the time that is used here is accurate at the millisecond level. Longitude, height are the most normal presentation of coordinates and the best presentation of coordinates, because we can tell from this a lot of things about the resolution and derive from it the accuracy of the data as well. The device may also provide speed, and for those interested, those particular coordinates are the top of Whitehall in London, just as an example. And then there'll be a whole table of this, potentially hundreds, potentially thousands, potentially tens or hundreds of thousands of data elements. So the file handling can be a problem, and the more you know about which bit you need to look at, the better, because you slice the data down to focus on the important elements. As well as the primary information of where and when the receiver and consequently the vehicle were, as much as how fast was it going, what was the driving style of the user, can be extracted from this, which it's not the collision information, but it's the information leading up to how were they behaving as they approached a collision. An example here is this is 10-second data. The car was traveling from the left to the right, and you see the timestamp here, 10:02.48, 10:02.59. So that one is 11 seconds, in fact, and then the remainder of 10-second spaced data. At each location, the device has provided a piece of speed information, which is derived from a Doppler measurement on the radio signal. And the second speed that I have calculated and added in this case is the speed between the data points. So in this 10-second gap, speed was 27.2 miles an hour, which kind of makes sense given that it was just under 25 at this point and 32 at this point. They're not always quite consistent, and sometimes the vehicle will have been, and I'm just looking for my example, which is hidden by some of your lovely smiling faces. There are cases where the speed, so on the right-hand side, I have an 11.2 and a 0.9. So it looks as though the vehicle was speeding up slightly, but in fact, the average between them was 18.6. So obviously the speed was significantly non-uniform in that case. But it does give us a small additional piece of information of enormous value and quantifiable reliability of how the vehicle was approaching a collision. Location accuracy meters. On the figure here is my derived figure based on extensive publications from the system providing authorities and hundreds of researchers who publish accuracy values for these systems. True location is at the center, a 0, 0, and then all of the dots are GPS fixes. So it's the unit's calculated position. The 1 sigma or 68% value is 4.8 meters. The one that I use most commonly is the 95% at 7.8 meters, so the larger circle. And then there are increasingly fewer points falling further away. So sometimes GNSS solutions will fall slightly further away, but this gives a very good view. Common that vehicle units and sports monitor equipment will perform better than that. So as I said, these are figures from the system provider, so they are based on the guarantees, based on the level of service that they've said they're going to deliver. But it turns out that their capabilities are improving over time, so they're keeping ahead. What they deliver is slightly better than the promise they've made. And that is combined with the fact that the receiver developers have worked out better ways of getting more accurate solutions. And so the performance is actually very commonly better than is shown in that illustration. Time accuracy is exceptional, is better than a microsecond for any GNSS fix. And so if you have once per second data, time tagged, the tag should be better than a microsecond. Normally it's not shown with 5 zeros and a 1, Normally, it is shown to whole seconds or potentially tenths of seconds, but usually that figure is precisely right. So the system is instructed to release a position fix exactly on a 1 second boundary. That is very common with these units. So it looks as though it has 1 second position, but in fact it has 1.000005 seconds resolution. GPS Doppler, so measuring the Doppler shift of a radio signal, can give us a speed accuracy of around 0.5 mile an hour at a kind of a best case. But it can be difficult, and by difficult I mean impossible, to tell whether that is reliable. We can derive speed from position, and we know the accuracy of the position. And if we do that, then it then depends on how accurately is the position measured and how accurately is the time measured. And in the example there, I have 100 meters traveled with an understood accuracy of 5 meters over a period of 5 seconds with an accuracy of 0.5 microsecond, would give me a speed of 20 meters per second plus or minus 1, which is 44 and a bit miles an hour minus 2.2. So pretty damned accurate for something like that. If we use smaller time intervals, the accuracy goes down. And for example, in the approach to a collision, it can be very interesting to look at not only smaller, but also larger time intervals to understand really how the vehicle was approaching a collision. So that's the best. The worst, the data may be spartan. There may be great big gaps in the data. They may be recorded every few minutes or once in a while. Now, in this case, my route was from Paddington Station in London down to the Royal Institute of Navigation, just east of the Albert Hall. But if the data I've got is here and here, did I go through Hyde Park? Or did I go around it? And that is an extreme example, but if you have spartan data and don't know the route, you can derive very little on the basis of that. Sometimes it's unclear whether the data is GPS data or something else. And I mentioned smartphones. Those of you with good resolution on your screens will be able to see a small yellow dot here. Now that dot is precisely, yes, GIS tools, that is precisely 7.8 meters in radius and is a 95% accurate GPS fix. The large circle is of radius 1.2 kilometers, which is typical and certainly not worst case for cell tower positioning, and covers a vast area, as you can see. Now, if all you get is location coordinates, and the system says, just to pick on Apple a little bit more, your iPhone system says, this is the precise coordinate, and this is a GPS fix, what shall we assume? Because it may well not be a GPS fix, it may well be a cell tower fix, because unfortunately that is simply the way that Apple has chosen to record that data. So it's an issue with mobile phones, and a thing that we need to home in on in the event that those are part of an accident investigation. It's never an issue with the sports equipment or the car telematics, but in the event that a smartphone is part of the investigation, that is a thing that needs to be looked at. The little tricks and traps there is Indiana Jones running away from a giant boulder. So I was just looking for something to indicate tricks and traps. postcodes as a telematics issue, and it's a very unfortunate telematics issue. Postcodes are scaled, so there are district, sectors, and unit postcodes, and there's 1 3/4 million unit postcodes, but that will cover several addresses. Quite often, and unfortunately, telematics evidence is presented as postcode. This is where the vehicle was, but that is not a unique location. It will have come from a GPS fix, but has been converted into a postcode, which is now as accurate as the postcode is, or as inaccurate as the postcode is. There is also what I call a process uncertainty. So we've gone from latitude, longitude, height derived by GPS, you've got reverse geocoding to create a postcode. And in some unfortunate cases, the insurance telematics industry is the worst at doing this. That postcode, the center of that postcode becomes the stated location. That's where the thing was, and that for crash investigation is it's told you broadly where the scene was, but the totally useful analysis, even though it is based on GPS. I've even been involved in a case where I'm pleased to say that I was on the side of the defense, but I was involved in a case where a speeding prosecution was being brought against somebody on the basis of movement between postcodes, and the only data available to the was the postcode data, and the telematics provider told them that that is all they had. So as you will imagine, the case failed because the data was entirely unreliable. Now, a GPS receiver will derive time when it derives location, and it will do so extremely accurately. And that's great. Unless somebody doesn't then take a very precise GPS measurement. I mentioned it, it's very common that it's produced exactly on the 1 second boundaries. It's not always done. And sometimes it's produced with a resolution of 6 digits or whatever. But somebody decides they don't want to provide 6 digits of time information, and they truncate it or they round it. Sometimes they use a different clock for the timestamps. So it's GPS data, but then they use a different computer clock to provide that data. So it's a thing that that can cause us problems. And of course, any time uncertainty immediately feeds into an uncertainty on the speed and the way of driving. The source of data should also be considered. Is it demonstrably legitimate? Is it traceable? For example, in the way the police have evidence to say it's gone from this point to this point, this is the way it's been stored. What is the reputation of the host who is storing that data? Could the data have accidentally been corrupted, or does the system include digital error checking on that data that confirms its veracity? And another thing to watch out for is that again, this is across is the fait accompli from an insurer where they provide a small picture, and the crash happened in this manner, and clearly it was Mr. Smith's fault. That has probably been sold to the insurers as an end-to-end solution that simplifies their life. and it probably suits one of the parties. So whichever party loses on the basis of that, it probably suits them, and they probably are going to back it. They very often don't provide justification, and so it may lack trustworthiness and reliability. They will have a whole stack more data, but there's a shortcut that this is often relatively often used to try to get around the detail. And finally, there's another thing to watch for. GNSS gives usually very accurate timestamps. Sometimes you want to compare that GNSS with something else. And things like CCTVs, they could have a GNSS in them giving accurate time. They nearly always don't have. And so they can be seconds inaccurate, or minutes, and sometimes hours out. They tend to have a very low grade clock. I mentioned the dodgy data sets, and I think I've beaten up Apple enough for one day in terms of complex data sets that don't always have an associated explanation anywhere, even if you get the National Crime Agency to write to Apple headquarters. And I suppose I should finally say that a little knowledge is very frequently dangerous in court. And of course, everybody, your supporting barrister, your judge, and everybody else knows how GPS works, or at least thinks they do. So
I think you answered this first question. Do all phones use GNSS chip, or do some pick up position from mobile phone masts? I think you covered that one in your discussion. That was the first one. Niall asked, can you explain the issue with 5G and aviation GPS in particular?
I'm not sure what Ian was referring to. Sorry, Nigel was referring to.
Niall. Okay. Perhaps he could come back to us on that, and I'll move on. How do you explain the overrun in the vehicle-borne GPS, where the vehicle comes to an abrupt halt, but the tracking system shows one position beyond where it actually stopped, as if it was a predicted course?
I nearly put that into the talk, and I chickened out because it's a slightly complex explanation that is different for different systems, and it goes down to the processing algorithms and the software that are implemented in the receiver. So the receiver and its carrying system is continually monitoring what it's been doing and predicting that it will do the same. So you end up with what we very often refer to as smoothing or filtering of a solution, where a new position is calculated, and from the previous position a new solution is also predicted, and the delivered solution is sometimes a combination of the two. Now, in the event of a rapid vehicle, in the event of from high speed to stationary very, very quickly, the prediction is on the basis of a significant continued motion, and is obviously completely wrong. Now, if that is given some weight in the algorithms and the software, then the delivered solution that includes that prediction looks as though the vehicle has gone past the collision and then returned to it. Yes, it is a thing that we say, and yes, it can be a problem.
I think that therefore it's explainable. Now you've given us that answer. I think you covered the next one, but correct me if I'm wrong. From Mike, you mentioned truncated data. How many positions to the right of the decimal point generally provides accurate positioning information? He's heard of 6 digits. I think you've covered that aspect in the talk.
I hope so, yes.
Yeah, okay. Phil, oh no, sorry, we're talking about loss of sound here. Let me scroll down. How do you find and cope with truncated data?
So sometimes it's obvious. Sometimes it's obvious because there is an end in the data. It's visible to the human eye that it's been truncated. Sometimes it can be detected because the data is clearly quantified. It's because of quantized. So we get this a number with let's say 4 digits after the decimal point, and the same 4 digits are apparent in other data sets. So it's been truncated. For example, it's been truncated as a radians angle and then converted into a degrees angle. And we see the same thing popping up. So it looks like when you plot it. So it may be simplest to identify by a plotting of the data and seeing a track moving along and then moving along, stepping.
Okay, thank you. Next one from Rob. Should we take data obtained from aftermarket telematics, the black box devices fitted to the car for insurance purposes, as being accurate? I think, again, you possibly covered that. If not, how do we verify the accuracy of the data and the tolerances to be applied to distances, time and velocity?
It's often very good. It's very often very good. We should certainly seek to understand what was the unit, and who is providing the data. So it's not it's not Arqiva, but it's the company that delivered the solution to them, and somebody else actually created the unit. So understanding what the unit was, who was the manufacturer of the unit, gives us an insight on how viable that unit may be. Some of them are produced by unnamed, typically Chinese manufacturers, and if they are unnamed, then they have an unknown provenance, and you give them appropriate credibility. If they are willing to put their name on it, then we can understand the reputation of that firm. What do they usually produce? What is the quality of it? And of course, one of the that should always be done is to plot the data and see how it looks. That gives us an insight into is it quantized? Has it got these stepping? Does the speed in other sectors away from the crash, does the speed along a motorway appear to be constant, or is that jerky because of unreliable positioning?
Okay. From Mike, do you use the Haversine equation to calculate distances and then use the GPS time to calculate average velocity between data points?
So I calculate distances on the basis of great circle calculations, which are closely related to Haversine. So there is the difference is extremely small. And I don't remember what mine are called anymore. I've now embedded them in Excel, and I plug things into those and out. But it's closely related to Haversine, and but it is that surface distance and then divided by the time.
Brilliant. Can you just explain how is a Doppler speed calculated and what vulnerabilities may need to be considered?
So the key measurement that we make on the satellites is this timing measurement that gives us a pseudo range, but we can also measure the frequency difference of that signal from what it should be. So we know the transmission frequency, we know the carrier frequency of the GPS signal as 1575.42 megahertz, and so we can compare the received signal with what it should be, and that lets us calculate the Doppler. So that is then the motion between the satellite and the user. Now, if we do that, I'm not going to get into the maths of it, but if we do that for a series of satellites, and we have the precise information on the satellite orbits, that lets us work out how is the user moving. So it is on that frequency difference. So the frequency will be different because of the satellite motion, but also the combination of multiple satellites gives us the user's three-dimensional motion. It's vulnerable because it's generally a secondary piece of information. So the receiver hasn't put the same energy into calculating Doppler as it has to calculating the position, the timing measurement, and generally nobody is looking for variations in the Doppler that might be the result of reflected signals from nearby surfaces. So we simply don't have a thing to compare it with that lets us get that additional accuracy that with a location fix, we can do the extra check of putting it on a map and seeing, does this location fall on the roadway, or does it fall on the roof of a house? That gives us that an extra reliance on that location.
Okay, thank you. Next one, instantaneous speed. How is that derived? The question being, surely it must be an average of something.
Doppler. So that is the Doppler measurement. So that is the frequency difference.
Yeah.
And it is instant.
Simple answer. If the device delivers a speed value, is it always based on Doppler measurement, or could it be based on the distance between two measured positions?
It could be based on either. It's important to understand what the manufacturer thinks they've done, because they're nearly always right.
Okay, and the next one, how can we assess accuracy of devices? Are there any published uncertainty values? You mentioned one based on 100 meters distance traveled. And how reliable are GPS dash cam devices, for example, Nextbase?
I've had very little to do with dash cam, and I don't know Nextbase. The location of the camera on the windscreen or close to the windscreen is a good location for signal reception, so it has potential to be accurate. Dash cams, of course, suffer the same as all electronic. There's a cost minimization, so they will use the lowest cost GNSS that they can get, which will be a mobile phone, one that was created for a mobile phone. And as I said, low cost is not the same as low quality, so it may well be a decent quality of unit. A dash cam is in a better position to receive satellite signals than many telematics units would be. So it could be very accurate, and I think you have to look at the data and see where you either have to look at the unit and do some proper measurements, or you can look at the measurement data and see where it falls on the road to assess its accuracy.
So in other words, it may be a good indication, but you don't take it on face value. Is perhaps the short answer.
Yeah. So at best case, it may be as good as a sports tracker.
Okay. I think this might be more of a statement than a question. 5G interferes with radio altimeters on planes, not GPS. The problem is that plane radio altimeters can have poor RF filtering. So whilst the frequency bands don't overlap and shouldn't interfere, there is concern that they might.
Well, I think that is somebody answering Nigel's question.
Yes, that's why I said I think it's more of a statement than a question.
And thank you, because they've
do any devices currently use dual band GPS receivers? Do you know?
I'm just being a little bit careful how I answer that. So yes, in our sector, no. In the world, yes, because the military use the full capability of the Russian military use the full capability of GLONASS and so on, and those are multi-frequency from a military perspective. Galileo is the first system that is coming along with a solely civilian capability. At the moment, there are very few receivers that we would encounter that use more than one frequency, and that is in the old days, that was because we were constraining the use of frequency. There was only one civil frequency available, so it was enforced because of that. These days, the issue has become using a single frequency is cost effective. If we want to use multiple frequencies, we may need specialized antennas or two antennas. If we have two antennas, we've got two connectors. There's additional processing and etc. So the cost goes up, and there's then a question of how much benefit is there at user level. So we presently will see almost no dual frequency equipment, and the exception would be those folks that get involved with precise GNSS measurements, survey grade equipment that does centimetric and millimetric measurements at a crash scene. That may well be dual frequency using specialized carrier phase processing algorithms that are, it's a different world. So their equipment is much more expensive, much more specialized, has to be specifically set up to take those precise centimeter and even millimeter level measurements. For the type that I was talking about, for smartphones, for sports trackers, for telematics, everything is single frequency and works.
Okay. Generally, how often is GNSS utilized following collisions? Is it mainly for fatalities? Do you know? Are there specific regions utilizing it? Will it be standardized and integrated into collision investigation moving forward, to your knowledge?
I'm sure it's the same for you guys, but I never get involved unless something serious has happened. So because we our work, mine and your work is has to be charged for. People don't call us for anything that is minor. So a serious collision, a fatality, is the only time that we would get involved, and therefore the only time that you would worry about what GNSS data is available. It's not standardized. The systems that create it are standardized, but the reporting of telematics data is in the hands of the telematics company. There are some formats that they can conform to, some good formats, and them deliver as postcodes. So work in progress.
I think the next one from Alan is maybe an answer to an earlier question, but I'll read it out anyway and you can comment. We use dashcam for traffic conflict research for edge cases for ADAS, and deliberately have a true time and GNSS stamp offset to render authorized grabs less usable for third parties, although locations can be identified from the image. But this could be unintentional in other dashcam users' setup. So I think that's probably an answer to an earlier question.
It sounds like, yeah, sounds interesting though.
Well, that's Alan Thomas. We can put you in touch.
Great, yeah, thank you.
Steve, in terms of plotting data on maps, i.e. Google Earth, often the vehicle is shown to the side of the road. Is this caused by a combination of mapping and GPS measurement errors? And that's a question from me too, because I've had the same experience.
So the maps, Google maintains, Google's primary database is very accurate, shockingly accurate. My experience has been that it's accurate to around a foot. And for those of you that don't use feet, 30 centimeters. It's agreement with, for example, ordnance surveys, precisely measured locations is generally accurate at that level, that 30 centimeter level. So the imagery that you see, so the Google Maps, I use Google Earth Pro mainly for my plotting, but Google Maps is also, and there's a selection of other tools. They have an Earth model that is accurately produced, and they project onto that Earth model imagery from satellites and aircraft, which is what you see as Google Maps when you see it with the photographic imagery. So it is very accurately rendered and also rectified to give a very accurate representation. Most of the time. There are particular cases when it is less accurate, but most of the time it is very accurate. If you see a GNSS track offset from a roadway, it may well be that the GNSS location is offset. So if you see a shift, so the GPS location is not a series of random dots. If you think of it as a combination of a bias and a random noise, that's a much more appropriate way of identification. So for a track going along a roadway, if it appears to be offset, it could be a GPS bias to one side with some noise as well, and that bias may be caused by the ionosphere through which the satellite signal is passing. If there are buildings on one side of the road, then or indeed both sides of the road, then those can cause what's called multipath, where the signal reflects strongly from the buildings, and the receiver is unable to tell what is the direct signal and what is the reflected signal. So its range measurement is now inaccurate because it's a combination of the direct and reflected signal. That can lead to a bias which can offset to the side.
The next one, I think, may be connected to what you've just said, but I'll read it anyway. Is there a method to fix map offset where route appears correct but appears in the wrong part of the map? I think you've just covered that.
I think I've covered it as long. I think I covered it as well as I can in a short space of time.
Yeah, but yes, okay. Are there any tips for discerning if it's an average speed or a Doppler speed being presented?
So the best tip I would say is always calculate the speed. It's easy to calculate the speed on the basis of the distance traveled divided by time. So calculate that yourself. If that has the remarkable coincidence of being exactly the same as their presented instantaneous speed, then their instantaneous speed is an average speed.
And right, there's two more. Can Dr. Dixon provide a very brief description of real-time kinetic GNSS? Yes or no?
Yes. Yes. Sort of all of what we've been talking about is ordinary GNSS or code phase GNSS. The signal, the GNSS signal in all cases is carried by a radio carrier, and going back probably as far as the 90s or even before that, the survey community realized that they could track the carrier of the satellite signal instead of do the usual processing on the code. So that community created specialized receiving. As I mentioned before, you'll sometimes see in crash scene reconstructions where you're making very precise measurements. It's appropriate for that, and the carrier is much more accurate. It's a very high frequency, and therefore, if you can tell where you are within that carrier, you can make a very precise measurement. So you can make a centimeter or millimeter level range measurement, and the combination of range measurements which are accurate at the centimeter level gives you a position that is accurate at the centimeter or millimeter level. There are then a whole load of extra tricks to play with that, because the carrier doesn't have markers on it that lets you tell which carrier. So one sine wave looks the same as the next sine wave, so you have to maintain continuous track on that to maintain an accurate solution. As soon as you lose track because of radio noise, obstruction, or anything like that, you've then got to redo that solution, and the redoing of that solution can take minutes or tens of minutes, which is why that approach to very accurate positioning is done by the survey community and not done by the rest of the world. It's much more accurate, but it's got that vulnerability to losing a solution and then having that great challenge of recovering it.
The next couple of questions, I think, I'll go back to the previous topic of offset and to your maps. Can an offset be caused by embankment as well as buildings?
Not in my experience. So a map, so a steep. I mentioned that Google Maps is in my experience accurate about 30 centimeters nearly everywhere. The one area where that fails is in particularly steep environments where the model that is used by Google or whoever is the map producer differs from reality. So their model of the map and then their overlaying of images on a map then starts to deviate a bit more just in that locale from from reality. So from that token, the map would be inaccurate, not the GNSS. I wouldn't expect the GNSS to be inaccurate in an embankment environment, except for the fact that some satellite signals will be lost because they're not visible through a mass of Earth.
Makes sense. Question that's worded, does that mean, I'm guessing the offset, it's safe to apply on a distance offset to position the receiver? For example, if it's known that a cyclist was cycling along the near side of a road in a rural location, but the map shows the cyclist traveling parallel but in the adjacent field. So in other words, I guess the question is, can you just plot it across to the road?
No, no. That's known as a fiddle factor, and that's not a thing for us professionals to do. We can identify it, and we can say that we believe that this is a bias, and then we have to try and explain why there is a bias there. But no, we should never squidge it across because that looks better. Okay, fine. The last one on here, is there any published literature recommendations? If there are any, that the sharing of that would be appreciated, and whether you're able to provide anything, and whether you want to do that by, I don't know, giving us a list of stuff that to put on our website. Yeah, I don't know whether it's on your website or what. I'll leave that with you. And the end of this question is probably from me too, is thank you for a very informative and well presented session. I think judging by the fact that there's still quite a few people listening an hour and 40 minutes after we started, that's great. Thank you very much indeed. And for those of you that are still online, the next presentation's on Wednesday the 25th of May at 10 a.m. GMT, and that's from a colleague, Art Speck in the Netherlands, and that'll be on extracting and understanding BMW's ZFS data. That'll be posted on the website soon. So once again, thanks, Chaz. Thanks very much indeed, and I'll say goodbye to everybody. Thanks a lot. Thanks for the opportunity, and thanks for your attention, guys. All the best.
Bye. Bye-bye.
Recording stopped.